Welcome to The Explainer. Today we're tackling a massive puzzle that shows up pretty much everywhere, from social networks to biology. And the puzzle is this: how do you understand the big picture of a complex system without getting totally lost in the details?
Think about it. If you need to figure out how one tiny change might ripple through a huge network, you can't possibly test every single little piece. So, what's the smarter way to do it? Is there a shortcut?
A really good way to think about this is vaccine development, right? You would never test a new vaccine on the entire population all at once. Of course not. There has to be a more efficient, a smarter strategy to figure out what its effect is going to be.
Well, that's exactly what we're diving into today, the mathematical version of that smart strategy. And to do it, we're going to be looking at vector spaces, which are really the fundamental building blocks of data itself.
So here's our game plan for solving this puzzle. First, we'll talk about the big picture strategy. Then we'll get our hands dirty with something I'm calling the vector recipe. After that, we'll follow a really interesting clue, the zero vector, to uncover some hidden redundancy. And that will lead us right to what we're looking for, the core set.
All right, first up, a strategy for everything. The whole goal here is to find a kind of shortcut, a reliable way to understand how any system transforms without having to check every single part. Now, to pull this strategy off, we're going to need a key tool. It's called linear combination, but let's just call it the vector recipe. It's basically a way to cook up new vectors from ones you already have.
So what is a linear combination? It's actually pretty simple. It's a new vector, let's call it v, that you make by taking some existing vectors, your u's, you scale each one up or down by some amount, and then you just add them all together. That's it.
So here's that recipe, broken down into 4 easy steps. 1. Start with your ingredients, a set of vectors. 2. Choose your amounts, which we call scalars. 3. You stretch or shrink each vector by its chosen amount. And 4. You just add all those scaled up vectors together and boom, you get your new vector.
This sounds way more abstract than it is. In fact, you do this all the time. Think about the vector 3, 4 on a simple graph. How do you get there? You just take 3 steps on the x-axis and 4 steps on the y-axis. That's a linear combination we use constantly without even thinking about it. Okay, so that's the basic recipe, but this is where things get really, really interesting. What happens when we use this recipe to aim for a very specific, kind of weird target, the zero vector?
This leads us to a crucial question. What kind of vector recipe gets you absolutely nothing? A vector that's just all zeros. Now, it might seem strange to aim for nothing, but believe me, the answer to this question is the key that unlocks this whole entire puzzle.
As it turns out, there are 2 ways to get to 0. The first way is, well, it's obvious. You just multiply every vector by 0. We call this the trivial solution, and honestly, it doesn't tell us anything useful. But the second way, the non-trivial way, that is the real clue. This is when you can get to 0 even when your amounts, your scalars, aren't all 0. When that happens, it's a giant flashing sign that there's a hidden relationship between your vectors. So let's really dig in to that interesting case, because what it reveals is something fundamental about our set of vectors: hidden redundancy. Let's look at a concrete example with these 3 vectors. Of course, we can get to 0 the trivial way, just multiply everything by 0. But look at that second row. If we take 1 times the first vector, add 1 times the second vector, and then subtract 1 times the third vector, we also get the 0 vector. We found a non-trivial combination. Bingo! So what does that actually mean? Well, if you just rearrange that equation a little bit, you find something amazing. The first vector plus the second vector equals the third vector. In other words, U3 is totally redundant. It doesn't give us any new directional information. It's just made up of the other 2. And of course, there's a formal math name for this. It's called linear dependence. A set of vectors is called linearly dependent whenever that interesting case exists, whenever there's a non-trivial way to combine them to get 0. It's really just the official mathematical term for redundancy. So if there's one thing you take away from all this, let it be this. When you hear someone say linearly dependent, all you need to think is redundancy. It just means at least one of the vectors in that set isn't really adding anything new to the mix. And this brings us right back to the beginning, to our final section, finding the core set. Because this whole idea of redundancy, well, that's the key to solving the entire puzzle we started with. The strategy we've been looking for turns out to be beautifully simple. Find all the redundant, linearly dependent vectors and just ignore them. What you're left with is your core, essential, non-redundant set of vectors. And this is the magic. This is why this all matters. By studying what happens to just this small core set, we can understand and predict the effect on the entire system. We don't have to test everything. It's maximum insight for minimum effort. It's the ultimate shortcut. Which, of course, leaves us with one last big question. We know the strategy now is to find this core, non-redundant set. But what does a perfect one actually look like? And more importantly, how do you find it? Well, that is the next exciting piece of this puzzle.